Hello, folks. I welcome you all to JK Tech Solution YouTube channel. Today, in our channel, I am going to walk you through the link budget analysis in RF communication systems. Before getting into link budget analysis, first we look through what is link budget analysis. So, the link budget analysis is nothing but the how much power is received at the receiver after traveling through the communication link. As you can see in the screen, the link budget formula, which is at the receiver, is equal to the power at the transmitter plus the gain of the transmitter antenna and the gain of the receiver antenna, and we need to subtract it with the total losses. So this is what about the link budget formula, which is calculated in dBm. So there are certain parameters which are required for link budget analysis. The first parameter that we are going to see here is frequency. As you can see in the screen about the frequency range of the different technologies. As you can see here, the 4G, the frequency range is of about 600 megahertz to 2.6 gigahertz. And for 5G, the frequency range is about 600 megahertz to 100 gigahertz. And for 6G, the frequency range is about 100 gigahertz to 1 gigahertz. Now we are going to calculate the link budget analysis for 6G communication. So for this, we have taken the frequency of about 300 gigahertz for both uplink and downlink. The next important parameter that we are going to see here is the wavelength. So as you all know that the wavelength is the physical distance between the two repeating point of a wave. So as we know the speed of light, which is equal to 3 into 10 power 8 meter per second, and the frequency that we have taken is 300 gigahertz, which is equal to 300 into 10 power 9 hertz, and we are calculating the wavelength, which is denoted by lambda is equal to c by f. So after substituting the above values of c and f, we get the lambda as 0.001 meter, which is equal to 1 millimeter. The next important parameter is link distance. The link distance is nothing but the physical distance between the transmitter and receiver in a communication system. So, whenever you consider the link system, there are two aspects that we can see here, that is line of sight communication and non line of sight communication. In LOS, this line of sight communication, there won't be any obstacles between the transmitter and receiver. If you take non line of sight communication, there will be some obstacles like buildings, trees, and so on. So in that case, we take non-line site of communication. So here we have taken the link distance is equal to 10 meter for both uplink and downlink. You know. Here the signal bandwidth is nothing but the range of frequencies that the signal occupies. So in our link budget analysis, we have taken the signal bandwidth which is equal to 30 gigahertz for both uplink and downlink antenna. So the next parameter here is the bitrate. So the bitrate is nothing but the number of bits transmitted per second. So now here we have taken the target bitrate is equal to 100 gigahertz. For example, if we take the target bitrate as 100 gigahertz, then the 100 gigahertz of data can transmit at a time and even receive at a time. So for that we have taken for both uplink and downlink we have taken 100 gigahertz as our target bitrate. Now we are seeing the modulation order. So the modulation order is nothing but the number of bits transmitted per second. It's not sorry, it's not transmitted. Number of bits transmitted per symbol. That is what modulation order. So here, what the symbol represents? The symbol is nothing but the unique signal that represents a group of bits. So that is what about symbol. And here we have taken our modulation order as you can see here on the screen for k. So modulation order is denoted by k, which is equal to 4 bits per symbol we have taken here. Like that you can take any case 8 bits, 16 bits. So here we have taken 4 bits per symbol. Then the n number of bits that we are going to take here is equal to 4. Okay. So the formula for number of signal levels is 2 power n. Okay, m is equal to 2 power n. So we need to substitute the n value in the formula. We get m equal to 2 power n, which is equal to 2 power 4. 2 power 4 is 16. So hence the m number of signal level is 16 level modulation. The next parameter that we take seeing in link budget analysis is code rate. So here the code rate is nothing but the ratio of the information bits to the total bits that are sent. So here as you can see the k is nothing but the information bits and k plus 1 is nothing but the total number of bits that are sent. So here, as we have seen in the previous slide, I have said the modulation order, that is k is equal to 4. So we are substituting that k value in the code rate formula. So hence we are getting 4 divided by 4 plus 1, which is equal to 0.8. This is the code rate for our link budget analysis. Now we are going to see about signal to noise ratio, which is very important. So signal to noise ratio is nothing but the ratio of the signal power to the noise power that we have in. So here, for calculating the signal to noise ratio, initially we need to know the data rate. So data rate, as we already mentioned in our previous slide, the data rate is about 100 gigahertz. Then the bandwidth is about 30 gigahertz. So from this, we need to find a SNR. So in addition to that, we need energy per bit to noise density ratio. So the value is constant, which is equal to 5. So we are substituting these values in the below formula. SNR equal to EB by N naught into R by BT. Here EB is nothing but energy per bit and N naught is nothing but noise density ratio and R is nothing but data rate and BT is bandwidth. So we are substituting the above values in the equation. Finally, we get the SNR is equal to 16.67. Next parameter that we are seeing here is free space path loss. So before getting into the formula, we need to know about what is free space path loss. The free space path loss is nothing but the loss of signal power when it travels to the free air medium. So that is what free space path loss. So we denote the free space path loss in dB. So here the formula for free space path loss is equal to 20 log chain of d plus 20 log chain of f minus 147.55. Here the d is nothing but link distance. As we already said, link distance is 10 meter. And the frequency we have taken here is 300 gigahertz. So we are substituting the uh, link distance and the frequency value in the above equation. After substituting, we get free space path loss, which is equal to 102 dB. So after finding free space path loss, now we need to find a total propagation loss. So in order to calculate the total propagation loss, we need to know two parameters. It is free space path loss. Then we need to know atmospheric attenuation. So already we have found the free space path loss, which is equal to 102 dB. In addition to that, we consider atmospheric attenuation is equal to 0 dB. So here the total propagation loss nothing but the sum of free space path loss and atmospheric attenuation. So we add these both values and we get the total propagation loss is equal to 102 dB. Okay, now after seeing the different parameters, now we are going to see about antenna design parameters. So here in this video, we have taken the antenna type as patch antenna. So for the patch antenna, as you can see, we have created a table. In this, we have transmitting antennas and then receiving antennas. So for transmitting antennas, we have considered for both uplink and downlink. For uplink in transmitting antennas, we have total 52 antennas, and in downlink, we have 512 antennas. Similarly, in the receiving antennas, for uplink, we have 512 antennas, and in the downlink, we have 32 antennas. So these are the antenna number of antennas that we have considered for both uplink and downlink uh, for the transmitting and receiving antennas. Now let us calculate the transmitter antenna gain. So as you can see here for uplink, as I already said, the transmitting antennas is equal to 32, and for downlink, the transmitting antennas is equal to 5 and 2. So to calculate the gain of transmitting antenna, we have a formula that is G of T, transmitting antenna is equal to 2.19 plus 10 log 10 of n. So for instead of n, we have here we have substituted number of transmitting antennas, which is equal to 30. So after substituting the value, we are finding the 10 log 10 value. Then after solving, we get 17.1 dBi as the uh, transmitting antenna gain for uplink. And for downlink, similarly, we substitute instead of n, we substitute 512, and we get the gain as 29.1 dBi for downlink transmitting antenna. Similarly, now we are calculating for the receiving antenna. So for receiving antenna gain, here for uplink receiving antenna, we have considered 512 antennas, and for that we got the gain value as 29.1 dBA. So similar to before calculation, we have done this calculation. And for downlink, we have taken receiver as 32. So we are substituting the n value as 32. We got 17.1 dBA as uh, as gain for downlink receiving antenna. Now we are calculating the receiving antenna power for both uplink and downlink. So now first we are going to calculate for receiving antenna power for uplink, which is divided by PR. So for receiving antenna, so RX power is equal to effective isotropic radiative power, which is EIRP, minus path loss, as we already discussed about the path loss, plus RX antenna gain minus RX loss. Okay, that is receiving antenna gain and receiving antenna loss. So as we have taken for uplink TX, that is effective isotropic radiative power for uplink TX, which is equal to 33.6, and we have taken the path loss, which is equal to 73 dB, and we consider RX antenna gain and RX loss is equal to 0 dB. So after substituting the EIRP and path loss in the above equation, we get RX power for uplink frame, which is equal to minus 39.4 dBm. So this is what the receiving power for the uplink antenna. And now we are calculating the receiving power for receiving antenna downlink. So here the receiving power, which is equal to effective isotropic, same formula, that is effective isotropic radiative power minus path loss plus RX and gain minus RX loss. So here we got EIRP value, we have taken 65.6. Then the path loss is equal to 85 dB. So after substituting the above value, we get RX power, the receiving power is equal to minus 19.4 dBm. Now we are going to calculate the noise power for antenna. So for noise power, we have a formula that is minus 174 plus 10 log 10 of B. Here the B is nothing but bandwidth. As I already said, that we have taken the bandwidth as 30 gigahertz. So now we are substituting the bandwidth value in the above equation, that is noise power equal to minus 174 plus 10 log 10 of B. So after substituting the we are substituting the 30 gigahertz, which is equal to 30 into 10 power 9 hertz, we are substituting here. So after substituting the above values, we get minus 69.23 dBm. So this is what the noise power that we get for both uplink and downlink antennas. Here we are calculating the noise figure. So first we calculate the noise power, and now we are going to calculate the noise figure. So here the noise figure for uplink is 12 dBA we have considered for receiving antenna, and for downlink, which is equal to 15 dB. But from this we are calculating the total noise power. So the total noise power for uplink, which is equal to 12 plus, in the previous case we have found for noise power, which is equal to minus 69.23. We are subtracting both the values. We got minus 57.23 for as a total noise power for uplink, and for downlink similarly we are substituting 15 dB plus minus 69.23 as a noise power. This total noise power, we need to add the noise figure and then we need to add a noise power. So by adding these noise figure and noise power, we get total noise power. So after adding this, we got minus 54.23 as a total noise power for downlink. So here you can see the receiving or receiving SNR, okay, receiving signal to noise ratio. So the receiving signal to noise ratio formula is PR minus total noise power. So this is what the formula that we have for this. Okay. So here too we are substituting for receiving signal to noise ratio. That is, we have already calculated the receiving power, which is equal to minus 39.4 for uplink. Okay, so for already we have calculated that value in the previous case, as you can see. And for n total, we got for uplink we got 57.2. So we are substituting the value, we got which is equal to 17.8 dB, which is nearly equal to 17.7 dB for uplink. So now we calculate the receiving signal to noise ratio for downlink, which is equal to minus 19.4 plus 54.2. In the previous case, what formula is that formula we used, and we calculate the receiving signal to noise ratio is equal to 34.8 dB. Now we are calculating and comparing the receiving signal to noise ratio versus target signal to noise ratio. So for that, margin is equal to receiving signal to noise ratio minus, we are subtracting both receiving signal to noise ratio and target signal to noise ratio. So for uplink, so our receiving signal to noise ratio is 17.7 and our target signal ratio is 16.7. So after substituting the value, we get 1 dB as a uplink. And similarly for downlink, we calculate using the previous formula, which we substituting value, we get 18.1 dB. Here now, as you can see here, the link budget analysis parameters that we have seen still now, I have summed up and we have given the table. So about all the parameters, unit, uplink, downlink, all the parameters we have provided here. Okay. So now let us move on to MATLAB for verification and validation. Now we have opened a new script in MATLAB online. So now let us verify and validate the parameters. Let us write the code right now. So initially I am giving CLC. So why we are giving the CLC is to clear the command window. For that I am giving CLC. Okay. The next line we are going to give here is to clear command. Okay. So why we are giving here the clear command is used to clear the variables and the memory that it occupies. So for that we are using the clear command. The next we are going to declare the frequency. So as I already said, we have taken the frequency as 300 gigahertz. So I am going to write it as 300 E9. Okay. The next we are going to write the lambda. So why we are finding lambda here is wavelength. Now we find a wavelength. So lambda is equal to 3E8, which is nothing but the speed of light divided by frequency. So frequency value we have already declared here. Okay, to find a lambda. The next we are going to see here is nothing but, so we are going to create a vector of numbers. So for that what I am using here is d. Okay, d is equal to linspace. Okay, so which is used to create a vector of numbers. So linspace of, so here as you can see here x1 x2 n. So here as you can see x1 is nothing but the starting point and x2 is nothing but the ending point, and yes, n is nothing but the total number of points that should be there between the x1 and x2. So that is what about the n. So now we can give the x1 as 1. Okay, sorry, it's yeah, 1, and we can give the endpoint as 10, and between that let me take it as 100 points should be there. Okay, so now we have declared this. The next we need to declare the gain of the transmitting and receiving antenna. So now let us take the gain of transmitting antenna, that is as GT. Okay, so here the GT, we have taken the gain of transmitting antenna as 17.1. Then the gain of receiving antenna, that is we have taken as GR. So GR is equal to, so let me use capital, GT equal to 17.1, and GR is equal to 29, 29.1. So that is what we have taken GT, that is gain of transmitting and receiving antenna. The next we are going to declare data rate, that is nothing but R. So data rate is 100 gigahertz, so 100 E9. Okay, next what we need to do, bandwidth. So bandwidth is nothing but what we have given the bandwidth as 30 gigahertz. So let me declare 30 E9. Next we are going to declare K, Boltzmann constant, which is equal to 1.38 into 10 power minus 23, which I can declare e power minus 20 minus 23. Then for the temperature value is 290 Kelvin. Okay, 290 I'm declaring here. The next so first I can have a command line so that you can easily understand. So here we have first declared the parameters. Okay. So next we are going to calculate the noise power. So for noise power, n, we denote n is equal to, as I already said the formula, so we just substitute k into t into D. So this is what the noise. And for dBm, we need to calculate the noise in dBm. For dBm, which is equal to 10 log 10 of n. So n is nothing but the noise plus 30. So this is what the noise power that we are going to calculate with this code. The next we are going to calculate EB by N naught. So this concept I already said in the video, so you can just check the video previous slides, so you can able to understand those concepts clearly. So next we're going EB by N naught values we are finding here. So for that EB by N naught values, just declare that value in the array. Okay. So for that we give M is equal to 4. So here I am giving here 4. We are calculating, we are going to compare them for 4 bits, 8 bits, 16 bits, 32 and 64 bits. So I'm just declaring it in array. So 4, 8, 16, 32, then 64. So this one I given. Then similarly we need to give it for EB and not. Okay, EB and not. So PSK, which is equal to 11, 14. So these are the values that we have taken for analysis. 23.4, 28.5. So this one we have found. So these are all the calculations that we have done. Okay, so first we have declared the parameters, then we have done the calculation part. Next we are going to plot those values. Whatever we have calculated, we're going to plot this. So here we are going to plot um, three figures. So the first figure we are going to plot here is transmit power versus distance. And the second we are going to do it for received power versus distance. And the third we are going to do it for frequency versus path loss. So these three parameters we are going to verify in this video. So first we can verify the transmit power versus distance. Transmit power versus distance. So initially we are going to plot them in figure. So I give figure first. Then I am going to give hold on. So as you can, as why we are going here giving hold on. So in order to plot multiple plots on a single graph or figure. So as you can see here, we have given for 4 bit, 8 bit, 16 bits, 32 bits, 64 bits. For that, I am giving hold on here. Okay. The next, we are going to give for I equal to. So we are going to run a loop here. I equal to 1 is to length of. Here we are going to take for 4 bits, 8 bits. So I am giving give it m. Okay. The next. So as I have already said, transmit power versus distance. So initially, in order to plot this, we need to find uh, free space path loss. Then only we can calculate the transmit power. So first we need to calculate the free space path loss. Free space path loss. So initially we are finding the free space path loss. So for free space path loss, let me take PL. Okay. So PL is equal to 20 log 10, 20 log 10 D. D I have already said length distance is nothing but the D plus 20 log 10 F. Here F is nothing but the frequency which we have taken 300 gigahertz minus 147.55. So this is nothing but the free space path loss. Next we are calculating the transmit power. Okay, so here we are going to plot figure for transmit power resistance. Let me calculate the transmit power. For transmit power, let me denote it as PT. So which is equal to, so here we are going to take EB and not. Okay, so EB and not. So it's coming EB and not of I plus the noise in dBm we are taking plus 10 log ton of or. So these formulas we've already seen uh, in the slide. Okay, that only I'm just typing here. Plus PL. PL is equal to free space path loss. I already said no, for transmit power we need free space path loss, so we have calculated the free space path loss minus GT. So GT is nothing but the gain of transmitting antenna minus GR. Okay, so this one we have done. So this is what about transmit power. So now we are going to plot. So plot. So we're going to plot for what distance, that is transmit power versus distance. So D comma mm, okay, we are given line width, okay, comma 2. Then we are ending this plot. Then we are owning the grid on. Then we are providing X label. X label. So we are labeling the X axis and Y axis. For that I have given X label. Let me take the X label as distance. Distance in meters we have taken. Next we are going to take the Y label. So the Y axis we are going to take here the transmit power. So in transmit power we are going to denote it in dBm. The next we are going to give the title for this plot. Let me give the title for this plot as transmit power versus distance. Here we have taken M array phase shift gain. So I am declaring here in the title. Then next we are going to give here the legend. For legend we are going to give here so for different plots I am going to give a legend, that is 4 PSK. Then we are plotting it for let me just copy here for easier. 4 PSK. Then we are going for 8 PSK. Then 16 PSK. The single quotation needed. Then we are plotting for 32 PSK. Finally, we are plotting for 64 PSK. Right, so we have given it in legend. So this is what the graph plot for transmit power versus distance. Now let us save the file and initially we can run it for transmit power versus distance. Let me run the code. Need to save. I'll just save it as link budget analysis. So let me save here. I think here we have made an error in 10 star lockdown should be provided. Okay, 10 star lockdown. Okay, so now we didn't get any error, as you can see here. Now as you can see here the plot for four that is MRA for 4 phase shift keying and for a 8-bit phase shift keying, then as you can see about 16-bit phase shift keying, then 32, then 64. So this is what the plot that we have obtained for transmit power versus distance. The next we are going to plot for right. So next we are going to plot it for the received power versus distance. So let me give comment that is received power versus distance. Now we are calculating for received power versus distance. So let me give similarly. I'm going to give figure first, then hold on. I've already said about what is the use of figure and hold on. You can refer that. So the next we are going to iterate in loop for I is equal to 1 is to length of sorry length of m. Okay. The next we are going to here we are going to find a path loss. Okay, so here we are now going to find a path loss. Um, so this is what we are going to find here. So I think we have already found the path loss. So we can take the path loss. Okay, I just copy the code from here, so it would be easier. Path loss. So here we found a path loss. The next we are going to calculate the um, transmit power. So already calculated. We just calculate the transmit power, which is independent of distance. Okay, that is independent of distance. We are going to find. Okay, we are going to find the transmit power. So here PT is equal to um, EB EB and not PSK of I. So now here we are finding what we have discussed in the formula. That's only we are finding here. This is equal for PR is equal to PT plus transmitted power plus gain of antenna plus gain of receiving antenna minus PL. This path loss. So for this we have found the path loss, then transmit power and receive power we have found here. Okay. Here we are calculating the receiving power. Okay. Received power. Okay. Let me take received power. So we have found we are calculating it for received power versus distance. Okay. Received power versus distance plot. Now we are plotting. Now we have found the received power. Similar thing we need to do here. Okay. Let me copy the code from the above one and I'll just okay. So now here we are plotting it for PR, that is receiving power. So let me give PR. That's enough. Then line with same to grid on. So here distance instead of transmit power, I need to give received power, which is in dBm. Then the title also we need to change, that is received power versus distance for MRA PSK. So remaining things were all same. Finally, that's it. So now we have written the code for received power versus distance plot. Okay, now we just run the code for received power versus distance plot. So let me run the code. Let me run the code right now. Run. Now as you can see here, the plot for received power versus distance. As you can see, whenever our distance is about 10 meters, so the distance varies from 1 to 10 meter, and the received power is in dBm. Okay, so as you can see, for 64 psk we got nearly about 10 meters, we got minus 137 dBm. So at received power we get some values for different bit psk. We get different values whenever distance varies, then the received power also varies. So as you can see here, the verified parameters in figure 2. So in figure 2 again, the transmit power versus distance is plotted, and the received power versus distance is also plotted. So now let me close this plot, and now let us calculate the plot for the frequency versus path loss. So this is what we are going to write the code. So that is frequency versus path loss. So this was the plot that we are going to plot right now. So here we are just changing the f range, f underscore range. So we're changing f range is equal to linspace. I already said what is the use of linspace. Linspace of 100 E9. So we have taken 100 gigahertz. So I'm giving 100 E9 to 500 E9. So here we are taking the total number of points to be 100. The next we are keeping d fixed, which is equal to 10. Let me restart MATLAB online. So we have a d fixed. Then so now the error was fixed. So now as you can see, we have given frequency range, and now we are going to find free space path loss, that is pl underscore sorry, pl underscore f, which is equal to um, 20 log 10 d log 10 d fixed. So these are all the formulas that I am writing it in the code, as we already discussed in the slide about the formulas. um, 20 log 10 f range, 20 log 10 f range minus 147.55. So this is what about the free space path loss that we have found here. The next we are going to plot the figure. So as I already said, we need to give figure. Then so here I'm going to plot. I'm going to plot here is for frequency is path loss. So we don't need hold on, because we are not plotting multiple curves. So I'm giving plot, that is f range. So we are going to calculate frequency is path loss. So f range in terms of E9, comma we are going for PLF. So already it's coming P path loss, comma now we are giving line width So line width I'm giving 2. The next I'm going to on the grid on. Next X label. So whatever we've done in the previous case, that only we are going to hear it. Going to do here. So X label is frequency in gigahertz. Then in Y label we are going to plot the in Y label we are going to plot the path loss. So in path loss we are going to calculate the path loss in dB. So then we are going to give title for this plot as uh, frequency versus path loss at 10 meter we are going to plot. Okay, right. So now we have written the code for plotting the frequency versus path loss. Now let us plot the values for all these three right now. Let me give the run command. So now as you can see here, we have obtained a plot for frequency versus path loss. As you can see at 300 gigahertz, we got the path loss as 102 dB, which earlier we have discussed. For 300 gigahertz, we get the path loss as 102 dB. So similarly, we have verified it for all the parameters that we have discussed at this transmit power versus distance. We have verified using MATLAB, using mmWave. Similarly, we have written the code and verified for received power versus distance for mmWave. And finally, we have successfully verified the parameter, that is frequency versus path loss at 10 meter at 300 gigahertz, in which we get the path loss as 102 dB. So finally, we have successfully verified the parameters. So thank you so much for patiently watching this video. I hope you to see you again on next video. Thank you. Have a nice day.